Okay, so we're live. Another problem to solve. I'd like to take a few seconds before we get into it. We'll just kind of hang out. Yeah. All right, let's get into it. Praise God for another day. Praise God for life. Yeah, let's jump right into it. Let's do it. Let's jump right into it. So we are looking at circular array loop. Let's see it. Let's see how we do. Playing a game involving a circular. No, Tony likes or dislikes. Not a lot more. Not as many like. Excuse me. Almost an even number though, which usually is not a positive thing. Playing a game involving a circular array of non-zero integers nums. Each num sub I denotes the number of indices forward, backward you must move if you are located at index I. It's playing a game. Okay, there's a circular array of non-zero integers nums. Okay. How many? Excuse me. How many positions you got to move if you're at index I? So, excuse me. If it's positive, then you're going to be moving forward. Negative, you're moving backward, which I'm assuming forward is to the right, backward is to the left. If our array is written left to right. Array is circular. You may assume that moving forward from the last element puts you on the first element, and moving backwards from the first element puts you on the last element. So, moving forward from the last element puts you on the first element. Okay, so it's circular. Gotcha. So we can perform our movements using modular arithmetic, right? Backwards from the first element puts you on the last element. Okay, fair enough. A cycle in the array consists of a sequence of indices SEQ of length k, which is actually kind of tricky when you're going backwards, by the way, when you're subtracting indices to make sure that you are positive. The way the modulo or division remainder function works with computers, it's different from the modular or modulo operator for the remainder, basically the remainder calculation for it's different from mathematics. So with computers, it actually doesn't work so nicely for negative numbers. It doesn't work as nicely. But we'll get back to that. Also, I gotta sneeze. We'll come back to that later. I have to both cough and sneeze at the same time here. A cycle in the array consists of a sequence of indices SEQ of length k, where following the movement rules above results in the repeating index sequence 0 to sequence 1 to sequence k minus 1 back to sequence 0. Yeah, so this is a pretty interesting concept. We've kind of explored this with a few different problems where there's like sort of cycles within the array. Although the cycles that we were talking about weren't really amounts that you're moving forward. It's actually or backwards. It's actually indices themselves. So like each index would tell you which other index you're going to jump to from that spot, which is kind of an equivalent definition to this, sort of. A little bit cleaner though, I think. Every value is either all positive or all negative. Oh, okay, it's a cycle only if it's I think it has to be in the same direction. So it's either all positive or all negative. Which, by the way, you could have these quote unquote cycles that have a different definition of the cycle, but you could have these cycles where it's not all positive or all negative. You could be jumping around all over the place. And k is greater than 1 means you have at least two values that you're moving back and forth from. Turn true if there is a cycle in nums, or false otherwise. Excuse me. So pretty interesting question. Very like, I don't know. It's kind of like very much defined within. It's kind of special, I suppose. The definition of the problem is very unique. So this is an interesting question. We'll see how we can do this. So I don't really know. I don't really know what to say with this. I don't know. I guess I gotta think about this. How do we efficiently find out whether or not a cycle exists? That's all they're looking for, is there's at least one cycle that exists. So so 2 so we start here, then we end up at 1, which then goes to 2, which then goes to back to 2. So 1, 2, 1, 1, 2. So that's a cycle, right? Index 0 to 2 to 3, back down to 0. And, 1 goes to 0, which then goes into a cycle again. 1, this actually is part of the cycle, so you go to 1, 2, 1, 2, back to 1. 2, go 1, 2. Yeah, it's also part of the cycle, and then this 2 is 1, 2. This kind of leads into the cycle, so to speak. So the deal is, if there is a cycle, so I guess part of the problem is, like, I kind of would expect there always to be a cycle, because you're either going to be looping over the same numbers over and over again, or they're not, in which case there's going to be a different number each time, but there's only a finite number of numbers, so at some point you're going to have to see one of the previous numbers you've already seen again. So there's got to be a cycle somewhere, but there could be different kinds of cycles. So there could be a cycle that's just one element, you know, you're just going in the same spot over and over again. You could have situations where, excuse me, this cycle goes in back and forth. So you could have like a -1 to 2, which then goes to another -1, and that would create a cycle. But even though it's a cycle, it's not the kind of cycle that they've defined here. So interesting, kind of a challenging question. Like, my first instinct is just to see, like, can you? I mean, you could dump the whole thing into an unordered set, and then just like loop through, you know, see if you get like the first cycle you get, and so basically start from index 0, and you would operate, right, until either you get back to index 0 or you get to a position where we have two things, right? If you come back to position 0, if you come back to the position you started at, then you return true. If you don't, what could happen is you could end up, well, actually, that could just be the beginning of the cycle, what you're looking at. Really, if you come back to any of the values that you're looking at in that cycle, so I guess you have like a visited set that you're looking at, so that you store. So if you come back to anything in that visited set, you would return true, except if the thing that you're coming back to is itself. So if the number, and actually don't return true, you would say if the number you're coming back to is actually the previous number. So in other words, you went 0 steps, I guess. Let me just see. Yeah, it's possible to go 0 steps. Oh no, nums of Nevi is not equal to 0. Okay, so it's not possible to go 0. Okay, so that's actually not a problem. Kind of going back, or actually getting stopped at a cycle that just kind of reiterates. So actually, the only way that you could not have a cycle here is if the only cycle available has switching directions. So actually every position you start with is going to be part of a cycle, guaranteed. So you're always going to return back. The question is, once you return back, if there were along the way, if there were any flipped parities, so positive. So if the original value is positive, if you see any negative numbers, then immediately it's going to be a false, right? It's not going to be you're not going to return true. Similarly, if you start with a negative number, if you see any positive numbers, but what you're going to do is that each time you as you loop through your cycle, what's going to happen is you're going to remove from the set all of the. You're going to remove all of the numbers, all of the indices, and the idea here is basically you eliminated one cycle as not the kind of cycle you're looking for. Now you're going to operate on the next index, which is going to take you to the next cycle. Basically, each of these cycles, the one positive or negative, right? This, if we throw out this condition, each one of these things actually partition your array into subsequences, disjoint subsequences. So you can actually jump from one subsequence to the next by just remove all the elements from one subsequence, and then you'll start at the beginning of another subsequence, and you just kind of repeat. The only way for this to return false really is if all of those subsequences have a flipped parity of positive to negative, which is what we see in the second example. We see one of these subsequences, right? -1 goes to 2, and then 2 goes 1, 2 to back to 2. Yeah. So now what's interesting is, I guess I'm wrong about that. I actually am wrong. It's not true that every element's going to be part of a cycle. I take that back. It doesn't matter that this is nums of I is not equal to 0. It can be effectively 0 if it's equal to the array size. Then if it's actually not even the array size. If it's equal to some multiple of the array size, then it's effectively 0, because you just end up in the same position again. So I take back what I was saying. I was wrong about that. You actually can be. You can have a spot where you basically just keep looping back into the same spot again. Whoops, that's my mistake. So actually, in that case. Also, the ability to handle the negative values, so I have to come back to that. But my problem here is, let's cut this few problems. So actually, because you can have these loops that kind of end, you can have sort of like an initial trail that leads to that. So actually, we do have to modify the logic a little bit. Well, you can do something like this, where if that particular value or index is effectively 0, right? Modulo is a multiple of the array size, then immediately you can remove that from consideration, right? Because that's not you skip that index, go to the next index. If you have an index that jumps to something else that has a different parity, you can eliminate that starting index immediately. If it jumps to makes a few different jumps which ultimately end up at something that has a different parity, then you could eliminate all of those on the spot. If it makes it back to itself in a cycle, so either a parity that's a multiple of the length, or a parity that's a flipped parity, or opposing a polar parity, then those are done immediately. If you get into a cycle, so actually, yeah, for the cycle you don't want to check against the first element. You do want to have sort of a set of elements that you check against, and then obviously you remove all those indices once you sort of exit early from the set of things to consider. So if you do end up with a cycle though, and all the parities are the same, they just return true and you're done. And that's kind of it. And then if you run out of indices, return false. So it's pretty easy, I think, overall to handle this, to think about this. Could you do it in linear time complexity and no extra space? Oh no. No! I just figured out how to do it in linear time and linear extra space. Now you want me to do it in linear time and no extra space? What's wrong with you? What's wrong with you? No. No. Oh, come on. This is terrible. Oh, this is awful. I mean, you need like a skip set of some kind. How are you supposed to do that? Oh no, I cannot do this without using extra space. No way. No way I could do this without using extra space. Huh. I don't know, man. Nope. Well, you can use cycle detection. You can use tortoise and hare cycle detection. Instead of using a set of things to see if you come back, right? Like you do that kind of thing. But the problem with like, yeah, those two conditions, really, if the parity swaps or if you hit a point that basically doesn't go anywhere, a dead point. Otherwise, everything's a cycle. Everything's partitioned into a cycle, one of these cycles. But the issue is, more significant and more important than that. Oh man. Oh no. Doing this with linear extra space is or constant extra space. Oh no. Oh no. Oh no. I really gotta think about this now. If nums of I is positive, move nums of I steps forward. Nums of I is negative, move nums of I steps backward. Huh. Yeah, think about this here. How do we do this without using any extra space? The problem is that if we follow, kind of end up jumping around. Well, I mean, there's a couple things, right? So, is it possible? Yeah, well, yeah, okay, no, not that either. I was thinking, if you removed all this, if you didn't have any zeros, actually, you'd still need to check. You would have still have that partition that I was describing, where you still could have things that have negative values in there somewhere. But just because there are negative values in there doesn't mean that you couldn't still have a cycle that they're one of the cycles that they're looking for. You definitely can have like trailing values that kind of end up jumping into some cycle. But the cycle itself just needs to be all negative or all positive, one direction. They're basically guaranteed to exist. The only time they don't really exist is if you have cycles of size 0, right, where the value just keeps coming back over and over. And the other problem is that some of these supposed cycles can have negative, could be flipping from positive to negative. That's what makes this question interesting, is you have two kind of cases that make it maybe not possible, where you have one of them where they're flipping back and forth, and the other one where the cycle itself is very small. The question is, I realize we can eliminate some indices, but we can't necessarily eliminate. For starters, we can't, if we just kind of run through, sort of simulate one of these potential cycles, we can't necessarily eliminate those elements. You really can only eliminate the circular part, the cyclical part. Well, you can definitely eliminate the things that lead up to that circular part, cyclical part. But actually, they don't really care about those either. You only really care about the cyclical part. And the cyclical part has to be totally uniform. Just thinking. And how? That's really challenging. That is really challenging. You can use the tortoise and the hare sort of problem algorithm, I guess, solution to find the cycles and even to find the starting points, and then to check the cycles afterwards to see if they're all positive or all negative. But the problem with that is, what if there's no cycle, right? When do you have no cycle? That's if the point you're looking at has, like I said, a 0, effectively a 0. That's really the only time you don't have any kind of a cycle. You could just stop right there. But then the question becomes like, well, you could have a whole lot of nodes values that just jump back to that 0, but they don't necessarily go directly back to that 0. They could maybe take up they could jump through half of the array before they go back to that 0. And if you have half of the array needs to traverse half of the array to get to that 0, that means you have a quadratic time algorithm, not a linear time algorithm, where nothing really gets you one of these cycles that you're looking for. And in order to determine that, you need to go through half of the array half of the time, most of the time, or more than at least half the time. At least half the array, at least half of the time. It doesn't even need to be half the array. It could just be a significant proportion. Doesn't even need to be that significant. It just needs to be some constant factor times n. Half is where it works too, though. Which you could easily do that, right? If you had just all ones is 0 and all negative ones. Or that would mean that at every point you'd end up at that 0, and you'd have to go through a huge part of the array to get there, or even just all ones and then a 0 all the way towards the right at the end. It's the amount of work you need to do to determine each of those indices are not good would be approximately linear, or the total amount of operations would be quadratic. Yeah, it would be the sum over I from I equals 1 to n, more or less. Or I equals 1 to n minus 1, which is big O of n squared, but it's still quadratic. I mean, it's not as bad as strictly n squared, but it's still pretty bad. Not sure if I should have you watch me blow my nose. Yeah. So, I mean, trying to figure this out here. So that's not really ideal algorithm to go like just the starting point by starting point. You can't really even do you can't even really do like okay, so you had this starting point and it didn't work out, and maybe what was like maybe you could eliminate some of those nodes, and sort of not try to process those again. And the problem with that is there's no easy way to really eliminate those indices from kind of jumping to those indices again. I guess what you could do is you could remark those indices in the original array as zeros, and then do it that way. Actually, that's probably a good way to do it. Basically, once you find out that the cycle isn't going to work, you just go backwards until the starting point and make those all zeros. I think that's the way to do it, yeah. So I actually think we're going to kind of hack this one a little bit, and we're not going to use extra space, but we're going to reuse the space that was given to us, and just destroy the space that was given to us. It's kind of hacked. I mean, it works, but it's there isn't really a better way. I can't really think of a way to do this that's like better than that. I'll probably have to look at the discussion, I think. yeah, quote unquote clever usage of the space that was given to us. But I don't think it's good. Like I don't think it really does what they're asking. But that's what we're gonna go for. So let's see if we can do this. Try. So we're gonna say int. Let's call it I guess, and then we'll say there's some conditions here. And the way this is going to work is we're going to there's a true, there's a false. We're going to, while I is less than nums.size, something like this, and ultimately return false. And we're going to say int, we're going to say slow as I, fast as I, and we're going to use cycle detection to find the next cycle within the array. And the way we're going to do this is we're going to say while slow is not equal to fast, which they're initially going to be at the same start. They're initially going to start at the same starting point. So you actually want to do a do while. And you're going to set slow equal to nums of slow plus equals nums of slow, or just equal to slow plus nums of slow modulo nums.size is going to be n modulo n plus n modulo n a little confusing how this works, but this should be correct. And then fast is going to be the same thing. Fast plus nums of fast. It's actually going to be, yeah, fast plus nums of fast. It's going to be, we're actually going to do this twice. We're just going to do it twice. So we have the initial index, we add to that index this amount, take that modulo n, because it could be negative, and then add n, and then take modulo n again. So the deal is, like, let's say we're at, like, we have 5 elements, and we're at, like, position 3, right, which is really the 4th position. And then we want to add like negative 1,000, right? So position 3 minus 1,000 is negative 997, which we want to take this modulo n. So we take a modulo 5, which is negative 2, I think, and then we add 5, and that puts us back at 3. Which is kind of interesting. So, yeah, which is exactly what we'd expect, right? Because when we go negative 1,000, it's actually a multiple of 5, so we should end up at the same spot. If we did negative 999, that would be 3 minus negative 199, which modulo 5 would be, I guess, let's say 5 times 3, so some multiple of 5. Well, let's see, 3 minus 999 will give you negative 996, which is negative 995 plus negative 1 quantity modulo 5, which is negative 1 mod 5, which is actually 4, right? Which you just add 5 at the end to, yeah, I think that's the right, I think that's correct. That's the right way to do it. Seems a little bit confusing, but I think it's right. Yeah. So anyway, that's how you handle the negative case. Is you just modulo n and then add n and then modulo n again. Because what this modulo n it'll be negative, the result. It'll be like negative mod 5 or negative mod n, and then this makes it positive mod n. And you actually don't necessarily. And the only reason why you mod n again is because if this was positive to begin with, then now you're just over n, and you gotta get rid of that n. But if you were negative, then this modulo n doesn't really do anything. So anyway, so we have our slow, we have our fast, right? We get our indices. While they're not equal to each other, we're gonna keep going, right? Keep updating them to new values. When they are equal to each other, so there's a couple things that can happen. Let's say so we'll say check also bool terminate early is false. So if nums of slow modulo n equals 0 at any point, really could do either of them, I think. You kind of want to do this check at every spot though. If nums of slow modulo 5 equals 0, terminate early equals true, and break. And we do that really every time, pretty much at every point. If either of these are 0, not modulo 5, it's modulo n. So this is kind of a tricky thing too. Not necessarily clear when you do this, where you do this, why you do this. Yeah. So, well, they're going to meet each other. If either of these are 0, they do end up meeting each other anyway, so it really shouldn't matter. You just end up with a cycle of just size 1, where it's just repeating against itself. So it doesn't really matter that much. Like, you're going to find a cycle no matter what. So what you've got to do then is, okay. You can also do the terminate early here. Yeah, I mean, you can kind of do whatever you want. So so the parity is I would just say is negative or is positive. Cycle equals, we're going to say, so this really should be the same parity. Yeah, so we'll do nums of slow. If that's greater than 0, that gives you the current parity, and then the same parity we'll say is true. So two things. If if nums of slow modulo n equals 0, or nums of slow if the current parity is not equal to nums of slow greater than 0. Right? Then we say terminate early and break. Okay. What's wrong with, not what's wrong with this, but the problem with this is like, this is kind of a tricky thing to do properly. Slow as I, fast as I, terminate early, current parity, nums of slow is greater than 0. So what we'd want to do is, with this terminate early, we kind of would want to do like, terminating index, we'll call it. Excuse me. Yeah, terminating index is, and we're going to say skip indices that have already been determined. B that have already been ruled out. So if yeah, let's say if, or so really while really it's like a for loop, I think, quite frankly. Nums of I is not equal to 0. While it's equal to 0, we increment I. And then so we say if I is equal to nums.size, and we break. Yeah, skip indices have already been ruled out. Slow equals I, fast equals I, cycle function to find the next cycle within the array. Terminating index will start off at I, or beginning index, we'll just say. Well, actually, I doesn't change, so we don't really need to do that. Really, this is the final index, so we'll call it terminating index is going to be equal to slow. And then let's see if we break here, say terminated early, set all of those values to indices that will be skipped. Yeah, so if terminate early, then we're going to say for int j equals I, j is less than or equal to terminating index, increment j. It's actually not incrementing j, it's going to be j equals I, j is less than or equal to terminating index. J is going to be nums of, j is going to be this operation, except with j. We can maybe just, oops, whoa, throw that there, I guess. It's going to be j plus nums of j modulo n plus n modulo n. This actually could be on the same line, I think, yeah. You will eventually reach the terminating index, right? I mean, you necessarily need to. All of these are going to be effectively set to So we're going to say nums of j equals 0. All right, remove all this by setting them to 0. Right, so you set all this to 0, and then I think you just increment I. Yeah, which makes I really just something in a for loop here. Interesting. That's if you terminate early. And the only reason you terminate early would be that's if you terminate early, and the only reason to terminate early is if you hit this terminating index here. The parity switches. Now, if you don't terminate early, what's interesting is a couple things. So you want to run through. You can find the cycle and check to see a few things. There's a few things to check. So we know if we don't terminate early that we're not dealing with a single loop, because this will terminate early on a single loop as well. If excuse me, whoa. I actually don't think you need to. I actually don't think you need to. I actually don't think you need to necessarily set this terminate early. I'll explain in a moment. But basically, if a legitimate cycle has been found, then check the parity of the cycle. Actually, necessarily so this is wrong too. Also, this is incorrect. Yeah, that's incorrect. So yeah, that's actually just wrong. That's wrong. You don't check the parity here. You check the parity within the cycle, only within the cycle. Part of the issue here is if you terminate early or if you don't terminate early. Does that really matter? Because that's the cycle anyway. Because I think this next check that we do here, I'm trying to say is this next check that we do here is going to check your cycle. Yeah, actually, we'll just do it this way. If you have it didn't terminate early, now I need to check the, and we're going to do some logic here, and then basically you're going to perform the similar routine. That's kind of what I'm getting stuck on. You perform a similar routine as if you did terminate early, but the difference here is that you're going to actually set your cycle here to all zeros. So you can kind of, it actually doesn't really matter which one of these you pick. You could start with slow. if you didn't terminate early and these actually met each other, you could set it to slow and then just loop through the cycle again, set those all to 0, and then set this terminate early to yeah, actually it doesn't really matter. You could yeah, you can actually just add this in here. That's fine. And then set terminate early to true. Right. Yeah, it doesn't really matter. You won't have a terminating index. Just thinking. This is kind of wonky. How are you not losing your mind? He does every day. I do something small too often. I have to change it up. What's up, Yuki? Welcome back. Hello, hello. It's different every day. I wouldn't call it small either. But who says I'm not losing my mind? Where'd you get that assumption from? Who told you that? Who lied to you? No. I don't know. I don't have too much to say. Let me finish the problem first, and I'll come back and chat about my hopes, dreams, goals, and ambitions. But yeah, because I'm actually struggling with this problem, so I gotta kind of think it through. It is really awkward though. I'm trying to handle this. I'll say that it's really way too awkward. Yeah, so we'll clear the cycle here, and then we'll set terminate early to true, and this will clear up to the cycle. But the only issue we have is this terminating index. I guess we'll just set that to int max, or we'll set it to n. Actually, less than or equal to isn't right either. It's actually got to be exactly equal to, because these indices jump all over the place. So because there are kind of path or cycle or whatever could be just all over the array. So it's actually got to be exactly. So this so actually we should set this to -1. So this will loop infinitely here if we don't set it to the right index. But this is the part that it'll sort of break on. It'll eventually reach the beginning of the cycle, and in the cycle. So here in the cycle, we're going to set the whole cycle to 0, or we're going to return true. And then we're going to set terminate early to true, which is a little bit awkward because that basically means that terminate early is always true. And we're always going to enter this loop because we're always either going to exit with a return true or enter this block, which means we really don't need this terminate early anymore. That's kind of what I was getting at before. I was trying to think that through. That's not really necessary. We just decide whether or not we pick a terminating index, if there is one, and so then we don't really need this either. But I guess part of the problem is that whether or not we enter this block in the first place, there's even a cycle to look at, is a question. And I guess there always is, sort of. Yeah, that's fine. Because we'll just end up setting this cycle to 0. And by the way, not just 0, it's actually modulo n is 0. Yeah, confusing. I realize confusing. So we check the parity of the cycle, which basically means we're going to set bool current parity to nums of slow greater than 0, and we're going to say while, and we're going to say int initial is slow, and then we're going to say while or just do while. Initial is not equal to slow. We're going to update slow each time. And we're going to say each time we do this, we're going to do, let's do, we'll use a pointer actually. We'll just do int temp equals slow, right? Then we're going to update slow, and then we're going to say nums of temp. We're going to set that to 0. We're going to say update to the next value. You're going to say if current parity is not equal to nums of slow greater than 0, then check will be true. And you're just going to say check and equals this piece. And we assume that we're not going to make it. So we always set this to 0. Nums of temp to 0. And we actually let's do it this way. Next is going to be this guy. We can do this on slow. Set nums of slow to 0. We're going to do next first, calculate the next value, perform the check on num slow, set num slow to 0, and then set slow equal to next. Update it to the next value. Okay. And we say if the cycle had the same parity all the way through, then we return true. Alrighty, something like this should do it. Now there's one more issue here, one more problem, and that is oh, this should also be not equal to, by the way. If it's not equal to this terminating index, then we'll keep looping. Oh, that's confusing. It'll never be equal to that terminating index if we set it to -1. Whoops. Uh-oh. 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 But actually, and it's not equal to 0 means that if this is equal to 0 and this is false, it doesn't matter if this loops forever. So this whole part will loop forever if you don't have a terminating index. But this part won't loop forever because that part that we got to over there will be set to 0. This cycle should be set to 0. And so this will be false as soon as you reach that part. So we'll keep going until that. Yeah, I think this is correct. Okay, also did this wrong too. This should be, I don't know. This part is kind of moved down. Part of the issue here, no, this is fine. This said nums of j equal to 0, so nums of I will always go to 0. Okay, good. So even if we are terminating index and this part of everything here is like, I don't know, if we somehow miss everything, this will still get set to 0, the j equals I part. Okay. One more issue is this check returns true, I think, when we run into if there's a terminating index. So yeah, we can do your check is always going to be false if we terminate early. Yeah. So that's going to be terminating index not equal to -1. Or it should be equal to -1, or it starts off true. So that's one more problem. Unidentified, undeclared identifier n. Oh, did it not? Probably should use n there now. Something like this. Alrighty. Let's see how this goes. Oh, while, do while. I forgot about that. I guess we'll put a space in with our while. I don't know. Okay, false, true. Nice. All that coding, all that thinking, all that trouble, and we're wrong. And we're wrong. Nice, perfect. Hold on a second. Okay. Oh, my neck. Ugh. 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 So the question is, why is this wrong? Output false, expected true. So 2 should go 1, 2, 1 should go to 2, 2 goes to 1, 2. So this this cycle should immediately, so terminating is -1, terminating index is -1. These eventually end up being equal to each other. So the slow goes to this index, fast goes to this second, this one, and then this one. Apply 1, apply 2, and then slow goes here, fast goes here, here. 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 So they meet at the first index. Okay. They're never equal. None of this never happens. Then we say initial slow. While initial is not equal to slow. Next, current parity is true. Terminating index is -1, which it is, so check is true. right? So check is true. Current parity is true. Next is going to be to this guy, to 1. Check the parity of this, which is true, true, and true. Excuse me. Uh-oh. Check is if it's equal to the same parity. That's my mistake. This check should be true. This check should be true. There we go. Okay. Slight misstep there. Misprogrammed that part, what that was supposed to do. The intended portion of that there. Runtime error. Okay. Alrighty. What happened there? Let's see, is it the second one? It's the second one. Okay. Why the second one? Now the question is, why does this happen? What happened here? What happened here? Well, we get -1 goes back to 2, right? Slow, fast, terminating index. Excuse me. Slow, fast, terminating index. So slow, we're at -1, and fast. So -1 goes to 2, which actually is directly here. Terminating index becomes 1. So -1. So 0 plus -1 modulo 2 is -1 plus 2 is 1 modulo 2 is 1. 0 actually. Uh-oh. No, modulo 2 is 1. Still 1. Yeah, it's 1. So nums of 1 modulo 2, 0. Terminating index is slow, which is 1. I realize it's a little bit confusing, so actually we just immediately break. And then we say initial is slow, which is this spot. Current parity is true. Check. This should be false, right? So check is false. Doesn't matter what we do in here. We're gonna be false over here. However, you can actually do a few things. I don't know. Do you slow it all down here? No, you don't. You actually should just check. No. I'm sorry. I take that back. We need to go through the whole loop. So this loop now should be set to 0. Next is 1 plus 2 modulo 2. So next is itself. Set num slow equal to 0, and then slow equal to next. So it'll be set to 0 over and over again. Interesting. Oh, well. And we just have to do end nums slow modulo n is not equal to 0, right? Because that's kind of the situation we find ourselves in. Oh. What? Hold on. Isn't this the one that's causing us problems? What happened here? What happened here? Check. While initial not equal to slow, which they're not equal to each other, right? Slow is, oh no, they are equal. Wouldn't they just break here? So this is not the problem. Actually, that doesn't matter. It didn't move anywhere. It's this one that's the problem. Huh. Who would have guessed it? Who would have guessed it? Check, check. Oh? Not even that one, huh? Where's the problem? What is going on? I gotta sneeze again. So actually, it's up here. Huh. I would not have guessed it. What is going on? What has happened? Oh, duh. Oh, oh, okay. It's this one. It's this one. I is less than n. That's what happened. I'm missing that condition. Okay. That's kind of interesting. I kind of didn't think about that. That's like such an obvious check, I guess. You wouldn't even think to check to make sure that's there. So actually my idea seems to be correct. My ideas seem to be correct here so far. I don't want to jinx it here. I don't know, I guess we'll just throw some random things in here. Oops. Yeah, this also was my job for a while. This thing, sort of, because I wanted to be a software developer. As far as like answering your question there, Yuki. Yeah, I wanted to be a software developer for a while, so this is part of my employment. This is part of being employable, was being a proficient, basically a competitive programmer. That's kind of what this comes down to. Like, so if I wanted to get hired by Google, that's what I wanted to do previously, would be to pretty much solve all these problems on this website would be the way to do it, or part of their interviewing process preparation. So yeah, this is kind of just what I do, I guess. Sort of, at least for a while. For me, it's a little bit harder. Like, some people only do it for like a few months, where they just grind this really hard. But for me, I'm just a little different. I don't really have that much time to do it like that. And I also have, like, I don't know, I'm a little bit slower. You know, like, I'm not that fast with this stuff, and I tend to try to really go in deep and get like the right answers from time to time, and that takes me a lot of time. I guess something like that. I don't know. I guess I don't know. I don't know what to say about it other than like it takes me longer, I think, than a person normally would. But usually, what you do is you do like 25 of these problems a day. You take like 3 months off from work. Just do this one 25 a day every day for 100 days, and basically knock out all the problems on the site in like a short period of time. And you do that to become extremely proficient very quickly. But I don't really have the ability to do that, the time or the ability or the will or the drive or whatever you want to call it. So I'm just kind of slowly meandering my way through it. So it's taking a lot longer than it normally would. Like, it's going to take me like years rather than like a few months. Yeah, that's another part of it. It wouldn't look as like I don't know, crazy is the right word, but just I don't want to say soul-sucking, but it wouldn't look the way that it looks now if I was doing it kind of like how you would normally do it. Just want to make sure the. Oh, so yeah, did I? Yeah, I think the parity thing I got correct. Yeah, that's interesting. So we do 1, 2, -1, right? How about that? The parity changes. I don't know, man. I don't know, I'm just trying different stuff here. I don't know what to even test. Seems to be correct so far. There's got to be something that I missed, though. Yeah, there's no empty ones. There's smaller ones. None of them are kind of zeros. Can we do like 3, 3, -3? How about that? What does that give us? Okay. I don't know. What about 1, 2, 3, -2? How about that one? I don't know, man. Do we just go for it? I think we just go for it. It's bound to be something wrong. Oh, hey, we got it. Sweet. Nice. Okay. Hey, awesome. Let's see if we can get something faster. It's so slow. It's so slow. Why is it so slow? No, come on, really? I spent all that time. It's so slow. Oh, well, anyway. I thought I was so smart too. Yeah, well, this is linear time without using any extra memory. Maybe if I used extra memory, it probably would be faster. Okay, well, whatever. We got it. That took a really long time. Over an hour, hour and 15 minutes. Wow. Well, anyway, so I guess Yuki's not here because I kind of was like talking to him, assuming he's listening, but I don't think he's here. So, also, yeah, when I guess talking normally, it's like the volume is so high that the volume is so high that it like laughing in the microphone causes issues. I can see over here. You can see it goes red if I go ha 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 ha. Right? It's like it just gets destroyed. Just goes full red. I don't know, man. I'll be totally blunt. I have been considering like there's a few things I've been thinking about. So, oh man, there's so many things to talk about. I don't know if I want to talk about it here right now. I kind of want to end this video because it's already really long. But like updates with my life. Maybe I'll just make a quick video. It's just like life updates. What I'm thinking about doing. I'll do that. I'll make a quick live stream. It's just life updates. How about we do that?